Thank you, Paul, for that introduction, and hello, everybody. My name's Jo Bradley. I work for Stormwater Shepherds. We are a not-for-profit organisation, and we are intent on reducing pollution from urban surfaces with a particular focus on plastics. But my background is very much in SUDS and water quality, and the water quality elements of SUDS design. So what I want to talk to you today about is the elements of water quality in your SUDS design and the things that you really need to think about, the topics that we are finding coming to the fore more and more in recent months, that we all need to get a better grip of perhaps when we're designing SUDS with a view to reducing pollution. So the four things I want to talk about are using the SUDS manual well, and using all of the SUDS manual to design good water quality treatment elements, making your device big enough, designing your devices well and building them properly, and maintaining treatment devices. The first point really is around the use of the SUDS manual. So you'll be familiar with chapter 26, which is the water quality chapter, and I know we're all very familiar with the tables in chapter 26, and the point I want to make really is how important it is to use the whole chapter. So the tables are very useful. They allow us to design SUDS treatment trains using the simple index approach, which I'll talk about shortly. But also in the chapter there is lots of other information in there about design criteria, using the different devices in the right order, making sure you protect groundwater, making sure you take good account of gross pollution loads that may come into the design. So my first plea during this presentation is to please make sure you use the whole of chapter 26, and if you've got a little time over the Christmas break, perhaps you could sit down and give it a read again, because I think we all read it when the manual first came out, and perhaps we haven't read it again for some time. So what the SUDS manual does is it asks you to take your development and break it down into areas according to their pollution risk. So look at your development. It might be a primary school with a car park, or it might be a retail shopping centre, and you look at your development and you identify areas that are at low risk of causing pollution, areas at medium risk of causing pollution, and areas of high risk of causing pollution, and identifying those different areas across the development before you start your SUDS design. So low risk surfaces will be things like pedestrian areas and off-road parking outside houses, and pedestrian walkways and cycle tracks where there's very little pollution source. There's just people walking and dogs, and perhaps bicycles, and there's very little source of pollution, and so water quality is those are low risk for a water quality problem. Medium risk surfaces are things like a supermarket car park. So you've got more traffic, you've got more movement of traffic, cars coming and going, changing gear, manoeuvring. If it's a B&Q car park, for example, somebody might spill something. So your pollution risk has gone up, and so these are medium risk surfaces. And then there are high risk surfaces. Now, high risk surfaces can have two different risks. They can have the risk of spillages, so there may be fast moving traffic or manoeuvring traffic or chemicals being moved around, so you have a spillage risk, but also you may have a high chronic pollution risk. And the biggest category in here for me, and what keeps me busy most of the time, are road surfaces with a traffic density greater than 30,000 annual average daily traffic movements. But most of the time I work with trunk roads and motorways where you may have 150,000 annual average daily traffic movements. So those surfaces are polluted because of the volume of traffic, the nature of the traffic, and you get pollution from tyre wear, exhaust emissions, spillages, screen wash, brake pads, clutch pads, all these different parts of vehicle manufacture. A lot of them end up on the road surface as you're driving and manoeuvring, and so that causes gross pollution, and we have to manage that accordingly. So in the SUDS manual, what it does is it puts numbers on that pollution for you. So you have what they call pollution hazard indices. So for every type of surface, the low risk, the medium risk, and the high risk, the SUDS manual provides you with a pollution hazard index for total suspended solids, for metals, and for hydrocarbons. So in table 26.2, there are numbers for those different pollutant types from those different surfaces, and they are unitless indices, and they just give you a measure of how polluted that runoff is likely to be. So for your development, identify the low, medium and high risk surfaces, and then identify the pollution hazard indices for those different parts of your development. Then you go to the next table in the SUDS manual, which provides you with pollution mitigation indices. So this tells you how much mitigation you will get for suspended solids, metals and hydrocarbons for different SUDS devices. So ponds, basins, swales, manufactured devices. And your job as a designer is to make sure that the mitigation index is equal to or greater than the pollution hazard index. And that's what the simple index approach describes. The simple index approach in the SUDS manual describes how you manage the pollution hazard indices and the mitigation indices to design a SUDS management train that will effectively deal with the pollution expected off that site. And it's that simple, the clue's in the name. So for low risk sites and medium risk sites, the simple index approach is adequate on its own. For medium risk sites which discharge to groundwater, you need to consider groundwater protection as well, and you will need to do a little bit more consideration. You might need to speak to the Environment Agency. And then for high risk surfaces, remember that the simple index approach on its own isn't good enough. So for high risk surfaces like waste transfer stations, manufacturing plants, industrial estates and busy roads, you will need to do more of a risk assessment before you can go ahead with your SUDS design. So for a road surface, you might use the risk assessment in the design manual for roads and bridges. For an industrial estate, you might speak to the Environment Agency and use their horizontal guidance for permitting, which describes the risk assessment process that you might use for those sites. If you were designing a petrol filling station, for example, you might use the Petroleum Institute's Blue Book because there's a risk assessment in there. So when you get into high risk surfaces, there will be other processes that you need to go through to make sure that your SUDS design is good enough to provide enough pollution control. But SUDS are still an option. It's not that there's a problem with SUDS, it's just that the design process has to be more comprehensive. The other thing to remember when you're doing the SUDS design and you're considering the simple index approach in the SUDS manual is groundwater protection. A lot of SUDS designs rely on infiltration devices, and I know we've already spoken about those in the previous session on water quantity, and I suspect we will speak about them again in the sessions on amenity and biodiversity. And infiltration is an excellent way of keeping the water on site, dealing with the water close to source, keeping the water at surface, all the SUDS criteria that we need. But you must remember, when your water is polluted, then you need to consider what will happen to that pollution and whether or not it will pose a risk to the underlying groundwater. And so groundwater protection is a really important component of SUDS design, and you need to consider it, and the detail of how to do that is in the SUDS manual. There are things to do. You can still infiltrate water to ground if it's polluted. You can have lined devices, so you can have a swale that's got a liner underneath, or you can have devices with a granular treatment media in the bottom that will catch some of the pollution before it infiltrates. Or indeed, you may find that the soil underneath the grass surface in your infiltration device is on its own enough to deliver pollution control, but you do need to check. So just very quickly, to bring that together, the important thing to remember is that if you're doing a low risk surface design for SUDS, your priority is going to be water quantity. So your priority for a residential development is making sure that it doesn't flood and it doesn't cause flooding downstream. The other primary pillars of SUDS for a residential development are biodiversity and amenity, making it a nice space to live, providing habitats for wildlife, protecting people's health and mental health, and providing green spaces. On a low risk surface, those are your priorities for your SUDS design. And actually, if you do those well, you don't need to give much thought to water quality. You'll run the simple index approach, you'll satisfy the requirements of the manual, and your SUDS design will be fine. So you might provide, for example, a pond with a sediment removal device upstream, and that pond will give you fantastic attenuation capacity. It'll provide amenity and biodiversity. It'll make it a beautiful place to live, and actually, as an aside almost, it will deliver water quality improvements. But on a medium risk site, you need to consider water quality equally to water quantity, biodiversity and amenity. So as we shift into a medium risk site where we know we've got pollution, then water quantity needs to come higher up the agenda, if you like. So you should have an equal balance really between the amount of design effort you put into water quality, water quantity, biodiversity and amenity on a medium risk surface. So you might end up with something like a bioretention zone, like the famous ones at Greener Grangetown, which deliver all 4 pillars of SUDS for a medium risk surface all in one device. And then for high risk surfaces, water quality should come first. So water quality should be your biggest design element, and you should put probably more effort into your design for water quality than you do for water quantity, biodiversity and amenity. So on these sites, pollution is a real problem and a real risk, and you need to bear that in mind and consider the design elements of that first, partly because you need to make space for the treatment of this polluted runoff, and you'll need to identify what space you need before you go ahead with the rest of the development. And so for a motorway drainage, for example, water quantity is very important, water quality is incredibly important, but actually in the middle of a motorway, you're not going to give any thought to biodiversity and amenity because it isn't relevant. And so you can see that on high risk surfaces, your design effort might shift a bit and really focus on water quality. So the 3 things I wanted to mention, as I said, make it big enough, design and build it well, and maintain it. So making it big enough is incredibly important, and I see small. I know Sue Illman calls them bomb craters, so small SUDS ponds at the bottom of developments that just I just look at them and think, well, they might be big enough from a water quantity point of view, but actually, if you genuinely believe that they're going to let the water rest and let the solids settle out, then they're probably not big enough. You need to understand the processes that are going on in your device that are delivering the water quality improvements. So sedimentation, the vegetation taking up pollutants, photolysis, breakdown of pollutants using sunshine through photolysis. Those processes have to have time to take place. So if you build a SUDS device that's too small, and the water whooshes through even in a 1 in 1 year 15-minute event, then that device isn't going to be big enough and it's not going to deliver the water quality improvements that you've assumed it will deliver. So the SUDS manual says you should design your device so that it copes with a 1 in 1 year 15-minute storm event, so that it treats the runoff from a 1 in 1 year 15-minute storm event. So work out what that flow rate will be and work out what that volume will be, and make sure that the device can cope with that volume of water and adequately treat it. It may be that you need to bypass higher flows around the treatment device to allow it to work properly. So certainly with proprietary devices, sometimes we'll say, yes, you can use a proprietary device here, you can use a vortex grit separator or a stormwater filter, but you need to bypass higher flows around the device so that it can work effectively. So you need to understand your flow rates for treatment and understand how your treatment device works. For high risk surfaces, I don't think that 1 in 1 year 15-minute event is enough. I think for high risk surfaces, we should be treating higher flows and probably a 1 in 5 year 60-minute rainfall event. And so if you're looking at motorway runoff, industrial estate runoff, waste transfer station runoff, heavy goods vehicle manoeuvring areas, so things like that, you need to think about spillage risk, which we've mentioned briefly before, but also how long is this runoff going to be polluted when it rains? And I can promise you, having stood at outlets from these sorts of surfaces taking samples, that the pollution persists for hours, 2, 3, 4 hours maybe, but you need to understand how much pollution you're expecting, how long you're expecting that pollution for, and what you're going to do about it. So make your device big enough. Secondly, I wanted to talk about designing it and building it properly. So I see SUDS devices that aren't designed very well, and I also see SUDS devices that are designed very well and then not built very well. And the 2 things are incredibly important. From a design point of view, for me, there are a couple of devices that deserve a mention. So tree pits are important in as much as we make sure that there's water going into the tree pit, enough water going into the tree pit. There is likely to be a significant shift in drought and water scarcity in this country over the next 40, 50 years. And we can't go around planting trees and then just letting them die. We need to make sure that the water goes into the tree pit or the bioretention zone, because we need to water the plants that we're planting. Woe betide, we should create habitat and then let it die. And so we must make sure the water's going in there. But also the water needs to go in there to get the water quality benefit. It's not going to get a water quality benefit if it just shoots past the tree pit and doesn't go in. The other thing is, if you're planting things as part of your SUDS design, you need to protect them. So make sure your trees don't get knocked down or run over. Make sure that your vegetation in a bioretention zone is cared for and looked after. So you need to design it so that it will be able to work in the future. You need to make sure it will last. And if you're building linear treatment devices like swales, it's really important to try and design your swales with over the edge drainage along the entire length of the swale. I see far too many where the inlets are periodically located along the length of the swale, but also I sometimes see them where the water comes in at the top of the swale and goes down the swale. If you do that, then you are concentrating the pollution in a very small space, and you're not using all the area available to you in the swale. So the grass doesn't get the opportunity to take the sediment out, and the soil horizons don't get the opportunity to attenuate the pollutants. So for linear devices, filter drains, swales, vegetated filter drains, things like that, you need to try and have over the edge drainage along the full length of the device to maximise the amount of pollution control you can get. And then maintain it forever. I've seen some horrific, well, it's really interesting, isn't it? I've seen some horrific examples of poorly maintained SUDS, but I've also seen some poorly maintained SUDS that actually have turned into beautiful habitats. So there's a big conversation to be had around that. But if you are going to build a pond that is designed to capture road runoff particularly, but any grossly polluted runoff, then you need to be really honest about that and say, okay, we're creating a habitat and then we're filling it full of noxious, poisonous waste. And that's not great. So I'm not keen on using vegetative devices for gross pollution. I'd rather the gross pollution was taken out first and the vegetative devices did polishing. You need to remember that if you're going to put gross pollution in a vegetative device, you're going to have to empty it. You will need to take the silt out probably every 3 or 4 years if it's grossly polluted, and that's really expensive. For heaven's sake, let's put sediment removal devices upstream of ponds and basins if the runoff is grossly polluted. In every example, we should put a sediment removal device upstream of a pond or basin, but very much so for grossly polluted runoff from high-risk surfaces. The other thing is, if we are building conveyance devices that are supposed to carry our runoff from one place to another, we need to maintain them. So I do see, in fact, I was out the other week on a site visit, and there was a drainage channel that was supposed to convey high-risk runoff down a drainage channel and into a watercourse, actually, which wasn't great, but that's what we were there to look at. But the drainage channel was blocked, and the water wasn't even going down the drainage channel. It was coming over the edge of the drainage channel into a field and then disappearing down a hole in the ground. We have no idea where it was going, so we need to do some work on that. But there's no point designing a conveyance device if you're not going to look after it, because if the dirty water doesn't get to the pollution control device, then the pollution control isn't going to happen. And any of you who are familiar with my LinkedIn page will have seen over the last 3 weeks, I've had this ongoing conversation about a detention basin in Preston that was built about 20 years ago and has never been maintained. And it's turned into a really pretty little copse, I suppose, with lots of willow trees and lots of scrub, lots of vegetation. And there's an ongoing conversation on LinkedIn to say, well, does it matter? It's not been maintained. It's no longer clear that it's a detention basin, unless you happen to know that it is, like I do. But actually, it's created this really, really beautiful habitat. So there's a conversation there around whether or not that's a good thing or not. I think the conclusion of the LinkedIn conversation is that actually we should have been honest from the outset and said that this is going to be a vegetated basin, a wild basin, or words to that effect, because it still serves the purpose it was designed to serve. The inlet and outlet structures are still okay, but its capacity will be compromised by the tree roots, the tree trunks, and so perhaps that should have been taken into account for the hydraulic design. And the other thing is, if you are using manufactured devices as part of the SUDS management train, so oil water separators, vortex grit separators, then for heaven's sake, empty them. So these devices are very good at capturing suspended solids. The suspended solids have most of the pollution stuck to them. So if you capture the suspended solids off a road surface, you'll capture most of the metals and most of the polyaromatic hydrocarbons at the same time, and the microplastics, because they're all in there in the sludge. So catch it, that's brilliant. These separators are very effective at doing that. For heaven's sake, take it out. So they need emptying probably from a motorway and trunk road every year or 18 months. For an arterial road in a town centre, perhaps less often. You might get away with emptying them every 3 or 4 years. And again, if you choose to use one on a residential development upstream of a pond, you might only have to empty it once every 7 or 8 years, but you do need to empty them. I can't tell you how many times I used to do petrol filling station inspections and ask for the consignment notes for the oil water separator to be met with a blank expression, because nobody had it emptied and there was no consignment note. So these devices are very good, they do a great job, but you know, empty them. They can be fitted now with alarms that tell you when they need to be emptied, and I think that's something that we'll see more of in the future. And then just as a reminder, really, that the last thing to say is about this protecting your capacity. If you build a SUDS treatment train or a SUDS management train, which includes attenuation capacity in a pond or a basin or even a tank, you need to protect that capacity. So if you've designed it for a 1 in 30-year storm event plus climate change allowance, but you let it fill up with sediment every few years, so every year there's 2, 3, 4, 5 cubic meters of sediment building up in that device, you're compromising that capacity, and that's no good, because the storm that you have designed that device to deal with will no longer be properly treated, properly attenuated. So it's a plea really from me to put some sort of sediment removal device upstream of attenuation devices, because I'm increasingly seeing that it happens, but at the value engineering stage, I sometimes see those devices being removed from the drawing, and we need to stop that from happening. So in summary, please use the SUDS manual in its entire, well, the chapter 26 in its entirety. Make sure you're looking at all the different elements of the design. Make your device big enough, and big enough for treatment, not just big enough for attenuation. Design it well, build it well, and then look after it. So thank you very much for listening. If you can find me on Twitter as @StormwaterJoe. If you want to follow me on Twitter, I have to say it's not all work related. I do tweet quite a lot about cows and sheep because I have a farming background. But also, if you have a look on LinkedIn, there's that quite interesting conversation about the detention basin is on LinkedIn in the last couple of weeks. Thank you very much.